Let's now tackle part C. So they tell us block 3 of mass m sub 3, so that's right over here, is added to the system as shown below. There is no friction between block 3 and the table. All right. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as in the original 2-block system. Explain how you arrived at your answer. So let's just think about the intuition here. If you think about the net forces on the system itself, they're the same as we had before. Now, the internal forces are going to be different. You're actually going to have two different tensions now that you have two different strings. But the net forces, the ones that are causing this thing to accelerate in the upward direction on the left-hand side, to the right on the top, and then downwards on the right-hand side, is still the difference in the weights between the two blocks. But now that difference in between the weights of the two blocks is moving more mass. And we know that force is equal to mass times acceleration, or acceleration is equal to force divided by mass. And our net force is the differential between the weights, or the difference between the weights of the block. But now we're going to be moving more aggregate mass. This is going to be m1 plus m2 plus m3. And so you're going to have a smaller acceleration. And so what you could write is acceleration smaller, because same difference in weights between m1 and m2 is now accelerating more mass. Accelerating more mass. And that's the intuitive explanation for it. And if you wanted to dig a little bit deeper, you could actually set up free body diagrams for all of these blocks over here, and you would come to that same conclusion. So let's just do that, just to feel good about ourselves. So on mass 1, what are going to be the forces? Well, you're going to have the force of gravity, which is m1g. Then you're going to have the upward tension pulling upwards, and it's going to be larger than the force of gravity. Let me do that in a different color. So you're going to have, let me do it. All right, so you're going to have this tension. Let's call that T1. You're now going to have two different tensions here because you have two different strings. Now the tension there is T1. The tension over here is also going to be T1. So let me do the same magnitude. T1. Now, since block 2 has a larger weight than block 1, because it has a larger mass, we know that the whole system is going to accelerate. On the right-hand side, it's going to accelerate down. On the left-hand side, it's going to accelerate up. And on top, it's going to accelerate to the right. And so if the top is accelerating to the right, then the tension in this second string is going to be larger than the tension in the first string. So we did that in another color. So I'm having trouble drawing straight lines. All right. So that we could call T2. And if that is T2, then the tension so then this is going to be T2 as well, because the tension the magnitude of the tension through the entire string is going to be the same. And then finally, we have the weight of the block. We have the weight of block 2, which is going to be larger than this tension. So that is m2g. Now, I've just drawn all of the forces that are relevant to the magnitude of the acceleration. If I wanted to make a complete, I guess you could say, free body diagram, where I'm focusing on m1, m3, and m2, there are some more forces acting on m3. m3 in the vertical direction, you have its weight, which we could call m3g, but it's not accelerating downwards because the table is exerting force. It's on an upwards, exerting an upwards force on it. So of the same magnitude, offsetting its weight. So That's if you wanted to do a more complete free body diagram for it. But we care about the things that are moving in the direction of the acceleration depending on where we are on the table. And so we can just use Newton's second law, like we've used before, saying that the net forces in a given direction are equal to the mass times the magnitude of the acceleration in that given direction. So the magnitude of the net force is equal to mass times the magnitude of the acceleration. And so we can do that first with block 1. So with block 1, actually, let me just do this with specific. So block 1, I'll do it with this orange color. So block 1, what's the net forces? Well, it is T1 minus M1g. That's going to be equal to mass times the acceleration. So it's going to be M1 times the acceleration. Now what about block 3? Well, block 3, we're accelerating to the right. We're going to have T2. Let me do it in that different color. Block 3, we are going to have T2 minus T1. Minus T1 is equal to M3. And the magnitude of the acceleration is going to be the same. Here we're accelerating to the right, here we're accelerating up, here we're accelerating down, but the magnitudes are going to be the same. They're all, I can denote them with this lowercase a. And then finally we could think about block 3. We could say that the net forces, well, that's M2g minus T2, that's going against M2g, is equal to M2 times its acceleration. And now, if we want to solve for acceleration, and this will be quite convenient, we can just add up all of the left-hand sides to get a new left-hand side and add up all of the right-hand sides to get a new right-hand side. And we can do that algebraically because they're all, this is equal to that is equal to that is equal to that. So if you add up these and then you add up those, well, then the sums are going to be equal to each other. And so what are you going to get? So if you add up all of this T1 is going to cancel out with the subtracting the T1. This T2 is going to cancel out with the subtracting the T2. And you're just going to be left with an M2g minus M1g, M2g minus M1g is equal to, and just for, well, let me just write it out, is equal to M1a plus M3a plus M2a. But we could, of course, factor the a out. And so let me just write this as that's equal to a times M1 plus M2 plus M3. And then we could divide both sides by M1 plus M2 plus M3. So let's just do that. So M1 plus M2 plus M3, M1 plus M2 plus M3. These cancel out. And so this is the magnitude of your acceleration. And notice, you have the same difference in weights. That's providing the net force on the system, but is now accelerating more mass. So you could even say, hey, look, I have more mass here. So more mass to accelerate. More mass to accelerate while I have the same net force acting on the system. We're not talking about the internal forces; those all canceled out when I added these equations. And so, if you're taking the same net force and you're dividing it by more mass, you're going to have a smaller acceleration. Hopefully, that all made sense to you.